In the next session, we will encounter Dr. Jignesh Valand, Department of Material Science, Sardar Patel University, Vallabh He has 15 years rich experience in academics, industry, and research and development administration at national and international level. His specialization includes nanomaterials, catalysis, composites, and expertise in R&D, T&D, lab commissioning, team leadership, chemical analysis, literature survey, research data compilation, instrument calibration, and problem resolution. He has UGC-sponsored startup grant for research project in the field of nanocomposites in 2018 to 2020. He was secretary of National Annual Catalysis Conference, CATSA 2013, at South Africa. He is reviewer of international journals like South African Journal of Chemistry South Africa, Carbon Letters South Korea, and Horizon Research Publishing USA. He has received postdoctoral fellowship Catalysis Project in 2012 and Research Associate Nanotechnology Project of Gujarat State Government 2005 to 2006. Addition to that, he has broad instrument handling expertise in SAM, TEM, TGA, DSC, TMA, XRD, universal testing machines, FTIR and UV visible spectrophotometer, gas chromatography, autoclaves, CVD reactors, bed surface analyzer, chemisorption analyzer, and many more. In his research contribution, he has 20 research publications in various national and international journals, as well as 2 book chapters in international publication. He has delivered 7 invited talks in conferences, workshops, and seminars. He has presented more than 25 papers in conferences and in research programs. Dr. Jignesh Walan.
First of all, I would like to thank Director HRDC Gujarat University and Coordinator of Refresher Course in Chemistry HRDC Gujarat University for providing me opportunity to share knowledge amongst colleagues and dear faculty members. I think this type of online refresher course has been organized by team of HRDC Gujarat University in the previous years also. So let's congratulate them for organizing such a nice refresher courses by online mode. Today, I'm going to talk on nanomaterials in heterogeneous catalysis. So let's start the talk on nanomaterials in heterogeneous catalysis. I am from Department of Material Science, Sardar Patel University, Vallabh. So when we talk about these nanomaterials in heterogeneous catalysis, these are all materials have a dimension from 1 to 100 nanometer. These all are materials. This is related with the size of the materials. 1 to 100 nanometer as a general aspect worldwide. And everyone knows about heterogeneous catalysis also. So these catalysts are homogeneous and heterogeneous. First, we'll start from the outlines of today's talk. So we'll see very recent literature on heterogeneous catalysis first, then introduction of nanomaterials, properties and applications, including this chemical reactivity of these nanomaterials are most important. That we'll see also. Introduction to catalyst and nanocatalyst with the catalysis, we'll see later on. And at the end, we'll focus on heterogeneous catalysis and its applications. So the recent applications also we'll see at the end of the presentation. So before I start, I have done some recent literature on heterogeneous catalysis. So first, I'm going to share amongst you the recent report which I have been gone through that we'll see now, and then we'll start the introductory part of nanomaterials. At last, we understand what is catalyst, catalysis, and types of catalysts. Will mainly focus on heterogeneous catalysis system. So let's start from the heterogeneous catalysis. Recent literature is available. Before that, we have to see how we can make chemical reaction faster. So we all know if we apply some heat treatment, so we can increase the temperature, we can supply some heat, then we can get the rate of reaction faster. But disadvantage is we require higher temperature and it is too hot. Another factor is pressure. By applying pressure also, we can get the rate of reaction higher. But explosions can happen, and we heard also in the past many accident happen because of or due to explosions. So we have to take care also. We can increase the rate of reaction by adding other chemicals. But at the end of reaction, this separation of chemicals, it is a tedious job. It is very difficult job to separate it out. So this catalyst came in the picture. Catalyst, we all knows it can increase the rate of reaction. But the disadvantage sometime, if we use the precious material, raw materials to make a catalyst, then the whole system is expensive, it is costly. So with this background, I'm going to show you the recent literature on heterogeneous catalysis, especially on heterogeneous catalysis. This slide will come in between also when I'm going to start the introduction of catalyst also or catalysis also. So at that time, we will talk again on this topic again. So this catalytic cycle is most important. When you see the step 1 in catalysis, the chemisorption is most important phenomenon. We all know about the adsorption, that is a physical process, and chemisorption, this is the chemical process. So by this chemisorption, the reactant on solid mesopore surface will come. A and B are the reactant. This mesoporous surface have a porosity of different materials. You can see here all mesoporous materials are listed in the table below. These all mesoporous silicates are also there. SBA 15, MCM 41. We all know about the titania, alumina, zirconia. So these all are mesoporous materials. Mesoporous materials have the porosity range from 2 nanometer to 50 nanometer. These are mesoporous materials. So these materials providing the support for metal particles. So metal particles are on the support of these mesoporous materials. This whole system is called heterogeneous catalyst system. So this chemisorption of reactant is possible on solid mesoporous surface of the materials, and then chemical bonding happen between the reactant and the solid support. After this step, we can get the product formation from the reactant. So C is the product that is on the support again, and at last, if we want to get the product, then desorption of the product from the surface with catalyst regeneration is most important step. So desorption is most important. So now we can see here the all materials are most important for making the catalyst. For making this type of heterogeneous catalyst, we can use many chemical methods, including sol gel method, solvothermal method, hydrothermal method, weight impregnation method, co-precipitation method is also very popular. So these all types of methods we can use to make the catalyst. And by making this catalyst we can use for different type of reactions. So out of all this material, if we can take the example of SBA 15, see here SBA 15 we can use for many chemical reactions like alkylation, coupling reactions, hydrogenation, esterification, and water purification. And different type of processes also we can use. For photocatalysis also we can use, for reduction and oxidation also we can use this type of SBA15. This SBA15 is a mesoporous silica support, and the metal particles, it can come on the support, and these metal particles can act as a active site on the support. This active site provide the reaction place where reaction occur on the surface. So the recent report in 2017 of heterogeneous catalysis, what they told, it can be used for the fuel cells, renewable fuels, renewable chemicals. Here we can see for biomass conversion, ammonia synthesis is very popular in the industry. Selective oxidation also, we can use the heterogeneous catalysis. So we can say that development of this type of active, selective, we can say hydrothermally stable and energy efficient heterogeneous catalytic processes is the key to sustainable future, because heterogeneous catalysis is the center of all chemical and energy industries. This is the center point. So this type of recently article is reported. This one is also very recent article published in 2022, and another article is published in 2021. Here it is showing you the life cycle of catalyst. Regeneration is most important term when we talk about this catalyst. So during regeneration, we can get the catalyst back, and that can be useful for the further reactions. So we can see here recovery of heterogeneous catalyst from reaction media, that is a back after the reaction. You can do recycling, and then you can do catalytic deactivation, because you are using the same catalyst again and again. Ultimately, you are getting the catalytic deactivation. So after getting the catalytic deactivation, knowingly or unknowingly, if we want to do or to use catalyst again, then we have to process with the regeneration procedure. So recovery of metal from the spent catalyst is also one option. We can get the metal particle back from the spent used catalyst, we can get it. So this is a kind of recycling, regeneration of catalyst or metal particles of catalyst. Another way, that one is reported in 2022. We can see the reference here, metal precursor synthesis. So you can synthesize the metal particle, then you can make the catalyst, and you can do the catalyst reaction. Ultimately, some separation process we can apply. We can apply, I think, many separation process we all know, that magnetic separation. We can do centrifugation, some sedimentation, filtration also a very good technique to separate the solid medium. Now this one we can apply, we can get the whole catalyst system, catalyst material back, or sometimes we have to do only metal recovery. If you are getting the all catalyst including support, that is catalyst regeneration. But if it not possible, we can go for metal recovery also. And the same metal we can apply, we can use to make new catalyst, So this kind of life cycle of catalyst, or we can say regeneration procedures, are most important nowadays to make our procedure eco-friendly and economically viable. Recent report in 2021, we can see here heterogeneous catalysis under flow for the 21st century fine chemical industry. So truly customer driven production is required. Easily scale up production is required nowadays. It is a time for the waste free, safe, by controlling all reaction parameters and procedures. And this type of approach is most important. So what I want to convey, that by using nanomaterials, people are making the catalyst. But from the recent literature, I come to know that after nanomaterials also, there are many recent articles, they are focusing on single atom catalyst system. So I am very happy to share amongst you these articles. These are the two articles. One is published in 2021 and another was published in 2018. So first of all, we should know what is a single atom catalyst. Single atom catalysts are defined as the catalyst in which all the active metal species exist as a isolated single atom, stabilized single atom on the support. That support can be porous, obviously, okay, and of by alloying another metal also. So we can use mixed metal also on the support, but it is isolated single atom on the support. So this system is known as a single atom catalyst. So single atom catalyst in which all metal species are atomically dispersed on a solid support. So this is very good approach in the present era. We can see the example of materials of single atom catalyst A, B and C. So first A is the schematic of single atom platinum anchored on a mesoporous alumina Al2O3 for the use in selective hydrogenation of butadiene, right? So here you can see there is a STM image in the figure B of isolated palladium atoms, substituted into copper surface, and that is used for selective hydrogenation. And the last example of oxygen reduction reaction for transition metal single atom catalyst. Here transition metal single atom catalyst is there, which anchored on nitrogen doped graphene. So the support is nitrogen doped graphene and they put the transition metal. So this kind of system of single metal catalyst is most important. In this whole catalyst, which we can talk for heterogeneous system, heterogeneous catalysis, the recent article in 2020, they gave very good examples of metal support interaction. Your metal is with many support. It can be oxide, we can say metal oxide interaction. It can be on carbon, metal carbon interaction. Carbon, like a carbon nanotube, graphene, etc. The metals can be on nitride support, that can be metal nitride interaction. So this type of metal support interaction is most important when we talk for heterogeneous catalysis system. So decreasing in the size of metal, it can be nanoparticle of metal, it can be clusters, and it can be in the form of single atom of metal. The catalytic behavior of supported metal species change significantly for various chemical transformation, And the metal support interaction, that is MSI, is very important, and it is believed that this MSI to play a critical and crucial role for the tuning of catalytic behavior for heterogeneous supported metal species. So this MSI is very important when we talk about heterogeneous catalysis system. The nanomaterials, now I am going towards the nanomaterials. As we have seen many examples, novel approach for heterogeneous catalysis. At the end of this nanomaterials information, we'll go again on catalysis in the same presentation. because first we have to understand what are the nanomaterials, and then after knowing the nanomaterials, its properties, its applications in various fields, including this catalysis, we'll again start in detail of catalysis and heterogeneous catalysis, including its application. But let's start on nanomaterials first. So as we all know that nanomaterials, these are known for its size. The nanomaterials describe in principle materials of which single unit that size between 1 and 100 nanometer. So this is the size between the 1 to 100 nanometer as a general aspect. We can call dimension between 1 to 100 nanometer. So nanomaterials are chemical substances or materials, we can say, that are manufactured and used at a very small scale. It means size. Since nanomaterials are developed to exhibit novel characteristics compared to the same material without nanoscale. So without nanoscale, we can consider as a bulk level, bulk scale. So we can compare the bulk material and nanomaterial in terms of properties. If we change the size, we can get significant property difference. Yes, it can be strength, it can be chemical reactivity, conductivity, or mechanical property. So in catalysis also, we are getting good activity, selectivity. The stability is also good for the catalyst if the size are reduced. So here, nanomaterials are most important for the catalysis system. So here, everyone knows about that millimeter, micrometer, 10 raised to minus 6. But now people are talking nanomaterial has a nano size, and that is 10 raised to minus 9. If you talk 1 nanometer, it means 10 raised to minus 9 meter. So the measurement standards are there, and international system of unit has a 7 base quantities: length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminance intensity. It has a different units are there from meter, kilogram to, you can say, up to candela. Now, what is relevant to the nanotechnology? So all are relevant to the nanotechnology. In particular, the unit of length at the nanoscale we can call nanometer. Okay, so here I already highlighted, you can see here nano 10 raised to minus 9. People will talk in future about the picometer also, 10 raised to minus 12. So this is the nano world. Each unit or nano size, if you can talk, who set the standard in this world also? In the nano world also, there is a standards. So who sets the standards? So International Standardization Organization, ISO, there is a technical committee 229. They set the standards on nanotechnology. So ASTM International Committee E56, ASTM formerly known as American Society for Testing and Materials. So they set the standard also for nanotechnology standardization for electrical and electronics products and system. There is an International Electrotechnical Commission, Technical Committee 113. They set the standards. So I put here the major organization who set the standards. I'm not physically there to take the lecture, but if I am there physically, then the distance between me and my colleagues sitting there in the class, it's around like 1 meter. So that is a you and me. And then millimeter, you can see pencil lead size. And then micrometer size, blood cell. And here is the nanometer, 10 to minus 9 meter. And that is we are talking for nanoscience. and picometer 10 raised to minus 12 meter. Let's see how small is nanometer. So if we take the example of human hair, obviously human hair diameter or thickness is vary person to person, but even though, let's take the example, it's where you can understand 70,000 to 100,000 nanometer, one human hair diameter or thickness, you can say like that. So it's like around 70,000 to 1 lakh nanometer size. And let's take the example of fullerene also. Fullerene is a C60. A popular name is buckyball also. So here is the world diameter 10 raised to 7 meter. You multiply by 10 raised to minus 8, then you can get 10 raised to minus 1 meter size, and that's like a football size, soccer ball size. And you again multiply by 10 raised to minus 8, you will get the size of 10 raised to minus 9 meter, and that is the size of C60, popularly known as buckyballs, fullerene. The third allotrope of carbon is a fullerene. Okay. So here there is a comparison from macro world to nano world. So macro world, micro world, and then nano world. So here you can get 1 meter size in the macro world, very big dimension in comparison with the nanometer. Then the world come micron, that is a 1 micrometer, 10 raised to minus 6, and it lasts 1 nanometer, 10 raised to minus 9 meter. At the left hand side, you can see the example from ant 5 millimeter human hair. It's very, as I mentioned before also, red blood cell 2 to 5 micrometer, and then DNA chain 0.5 to 2 nanometer size. So now here the right hand side, head of the pin 1 to 2 mm. Then here the some artificial examples are there. Quantum coral of 48 iron atoms, that is a 14 nanometer size, and you can see the picture. I think in the next slide you can see the bigger picture of this also. This one is like a simulated pictorial presentation of carbon nanotube. It has a one here, and one second picture is like a quant type geometry, and you can see the diameter of carbon nanotube is around 2 nanometer. So here are the example from left hand side also, and for right hand side also, from macro world to micro world, and then nano worlds. By this way we can understand how the nano world is there and which type of materials are there in the nano world. Best example is here, centimeter to nanometer. So what is nano? I put here reference also. You can highlight the square portion of human hand, and then the length is 10 centimeter. This is the real dimension, and then you can go, you can gradually decrease the scale up to 1 centimeter. You have this picture, gradually from 1 centimeter to 1 mm, then 100 micrometer, 10 micrometer, and gradually up to 1 nanometer. You can see the microstructure very well. So by this way we can decrease the size from centimeter to nanometer, and we can visualize very clearly with the help of different microscopes. Size at the nanoscale. This one is very good slide actually, and we can get the few very good examples how small nanometer is. So some examples are there. A sheet of a paper, simple paper, about 100,000 nanometers thick. Now imagine how small is nanometer. So human DNA, as I mentioned before in the previous slide also, 2.5 nanometer in diameter. So there are different examples, but you can see here 1 nanometer is about as long as your fingernail grows in 1 second. So this is like very good example. We can get at least the idea how small is nanometer is. There are different examples also. Viruses from 10 nanometer to 60 nanometer. Bacteria 30 nanometer to 10 micron sometime. Dust from deserts, fine dust. It has a size of around 100 nanometer. So we have a different example, combustion suits Paint pigments, these are also in nanometer. Diesel exhaust particles are also in nanometer size. People already analyze and they observe. Fullerene, just now we discussed about the buckyball, size is around 1 nanometer, and nanotubes, it's vary. You can talk for nanotubes, is a single wall as well as multi-wall. So it's vary, but again, in general, the nanotube has a 1 nanometer to 500 nanometer size, and length is also there for the nanotube. So semiconductor wires are also there. So there are different materials are there in the nano world, which has a nanoscale dimension. So now the question come, how these nanoscience or nanotechnology related with the different fields? Yes, the nanoscience and nanotechnology is related with different fields. Like you can talk for physics, you can talk now in the chemistry also for catalysis, for example. Only today's topic is only for catalysis. Otherwise, related with with many fields in the chemistry itself. But today we are going to talk only for catalysis. But it's the nanoscience and nanotechnology is related with the biology, material science, engineering, and technology. So this is like an integrated understanding and collaboration. Richard Feynman, Nobel laureate, he dreamed nanotechnology in 1959. There was an annual meeting of physicists in America, and at that time he gave the statement that there is a plenty of room at the bottom. At the bottom means in structural language, atomic structure. So there is a plenty of room at the bottom. It means people can think at atomic level, they can modify the structure at atomic level. He dreamed, he talked in 1959. At that time, people laugh on him like what he is talking, but it happened. It happened, and then nanoscience and nanotechnology progress started. So we can see here example, iron at the nanoscale. This is the real picture produced by IBM research in 1992, long back. But here you can see the one iron atom. I put here the indication that one iron atom is there. You can see here, very good picture. And this scale is showing you 1 nanometer, this black line. So you can see here approximately 3 atoms are there in 1 nanometer, in 1 nanometer size, 3 atoms approximately. So this is the iron at the nanoscale. So when we talk about nanoscience and nanotechnology, yes, before I talk on nanoscience and nanotechnology, we started from nanomaterials. Why? Because nanomaterials cross the boundary between the nanoscience and nanotechnology, and it links these two areas together. So what is nanoscience? Nanoscience is the study and manipulation of materials at atomic, molecular, and macromolecular scales. So basically science is a study of phenomena and manipulation of materials. Here you're talking for atomic, molecular, and macromolecular scales where the properties differ significantly from those at a larger scale. It means here is the clear comparison between the bulk level as well as the nano level. So you can talk at atomic and molecular level in nanoscience. Nanotechnologies are the design, characterization, and production and application of structures, devices, and systems by controlling shape and size on the nanoscale. So anybody can work, they can design, they can characterize, they can produce by using the knowledge of nanoscience, by using the nanomaterials they produce by using the nanoscience. But now there is a technology. So you have to control the shape and size at the nanoscale. So in general, we can say general aspect for nanomaterials dimension is in the range of 1 to 100 nanometer. Let's see now nanotechnology growth. Nanotechnology growth, the slide is very good. You can see here industrial revolution is there. You can talk for long back 1771 to 1851 is 17th, 18th century. there was a textile revolution. After that, there was a railroad, automobile, computer revolution. Everyone knows about that. It has started. It will continue also. It will continue. And then now there is a nanotech revolution. It was started long back, but it will continue for a long time. For a long time. So this is the nanotechnology growth, and that's why the present era is for nanoscience and nanotechnology. So the question will come in the mind, this nanoscience or nanotechnology is old or new? Yes, before the word nano was not used specially for those material have nanometer dimension or like that, but before there were the material, those have nano size diameter or dimension or whatever, length or whatever. So here stained glass windows, it contains the very fine nanomaterials. Silver halide photography, everyone knows. AR coated lenses, viruses are also nano machines. These related with the old nanotechnology. But if you talk about new nanotechnology, the designer drugs are there. There is a transparent sunblocks. Sunblocks are there, which contain the nanoparticles, very good nanoparticles inside. Now, designer drugs, everyone knows about the targeted drug delivery concepts. So, designer drugs are there. These all are related with the nanotechnology. Now we can or we are designing and manipulating at the molecular level, whereas before it was either evolution that did it for us or results happen which we never really understood and so couldn't optimize it. Before it was like that, but now everywhere people are talking for nanoscience and nanotechnology. So here also the best example you can see here, the glass in the Lycurgus cup, probably made in Rome during the 4th century, 4th century AD. And now it is there in the British Museum. It contains the nanoparticle of silver and gold. Particle of silver and gold it contains. This is the very old glass, Lycurgus cup. Okay, so now you see now what's happening actually. You can see here, it is colored green. But when held up to the light, the color changes to glowing red. You can see on the screen how it's changing its color. You put under the light. So by this way, nanoparticles effects you can visualize. So historical use of nanoparticles, stained glass and the Lycurgus cup. This cup is made up of dichroic glass that has colloidal gold and silver nanoscale particles in the glass. When held up to the light, the ordinarily green cup from the silver particle shows up red due to the gold nanoparticles in the glass. More informations are there also. It is there available at the British Museum. So now you can talk from these silver or gold particles optical properties. If you convert the bulk level particles at the nano size, actually you are changing the optical properties also. You are changing many properties, but now we talk for optical properties. Bulk gold appears yellow in color, everyone so golden color. But if you convert this bulk gold to nano size gold, then it appears red in colors, red in color. The particles are so small of nano size gold and that electrons are not free to move about as in the bulk gold, That's why nano size gold appears in the red in the color, because this movement is restricted. The particles react differently with light. So electrons are not free, movement restricted, and that's why it behaves differently under the light. And that's why you can see here golden color, bulk gold, 12 nanometer gold particles look red. This is microscopical image. By this way, the example of CDSE is also very popular. CDSE, 2 nanometer. If you change the size, If you change the size, the optical property is changing. So you can see the red color of 5 nanometer particle. This is computer simulation. This is not real particle, but real particle you can see now in the next slide. By this way, optical properties are related with the size of nanomaterial. CDSE nanoparticles less than 10 nanometer in the size under visible light and UV light. You can see the different color with respect to different sizes, and you can also study the optical absorption with respect to time. So you can see clearly here wavelength change with respect to time. So time and size both. So here, because of this, it's showing you different color with different size and wavelength. So optical properties are very important when you're changing the size. So by this way, from the bulk level to micro and nano level are very important concepts. You can see here, if you talk about mechanical property, I know we all are working in the chemistry field, but sometimes we have to or we have to gain the knowledge in applied field also. And that's why you can see here the hardness comparison, iron and copper. The cream color indicating for the bulk metal and the blue color is indicating from the nanostructure powder. You can see when you convert this iron from bulk to nanostructure, hardness is also increasing. Same thing happen for the soft copper. For the soft copper also, you are increasing the hardness when you convert from bulk to nanostructure. By this way, we are getting very big variation, or you can say change in the different properties. We took the example of optical properties. Now we are talking for mechanical properties, and the example is hardness, but there are many properties. You can talk like a surface area also. Surface area is very important when you talk about the catalysis. We'll talk later on, but now you can see here what's happening actually at the nanoscale. Here you can see now these are the particles, and this is the magic when we talk about the nano. You can say like big particle is there. You can consider it in a bulk form, bulk size. You can convert this bulk into micrometer size and then micrometer to nanometer. So actually what happening? Actually, you can see the red border. You are increasing, you can just consider is a surface area. And now you are ultimately increasing the surface area by mechanically grinding, or you can say like you are gradually decreasing the size by any method. I will discuss the different methods also in coming slides, but different method. And then by this way, we are increasing the surface area and ultimately the activity of resulting particles. So nanoscale materials have a far larger surface area than similar masses of larger size material. Similar mass with enhanced surface area. As surface area per mass of a material increases, a greater amount of material can come into contact with surrounding materials, thus affecting the ultimate reactivity. And this is very important concept which can be used in catalysis. So mechanical properties are also changing, as I told before. And in mechanical properties, the grain boundaries play a significant role in the material's property. Grain boundaries, there is a whole page equation is related with the mechanical properties. I will not discuss more about this, but at least we have some knowledge. It's affecting on the hardness also. It's enough for now. So here, whole page equation, you can see here that dislocation slip and grain boundary sliding. So this size is like very important, 10 nanometer. Gradually you can increase up to 10 nanometer the mechanical property, or you can say strength also. But after that 10 nanometer, some grain boundary sliding is happening. This is like general concept. So here from amorphous to nanomaterials and then conventional grain size material. But when we talk about nanomaterial, the hardness is increasing. It is maximum. with the function of grain size. You can see here the grain size. So this grain size is smaller, this is increasing. Ultimately, you are getting less hardness, very low value of hardness. So when we talk about the nanofabrication, how you can synthesize or fabricate the nanomaterials, the nanofabrication can generally be divided into two categories based on the approach. So based on the approach, you can say the top down and bottom up. So top down and bottom up are the two popular approach that can be used for nanomaterials fabrication. So nanomaterials fabrication, here when you talk about top down, then fabrication of device structures via monolithic processing on the nanoscale, and bottom up fabrication of device structure via systematic assembly of atoms. So in bottom up, we are progressing from the atomic level to nano level, nano size dimension material. And here the basic unit of a metal, you can say, but you understand now in the next slide very clearly. When you talk about top down and bottom up, so you are going from the top to bottom. And you talking from bottom up, you are going from bottom, from atomic level to top, but not at bulk nano size. So here bulk material, for example, as a raw material, you are taking raw material and then you are converting those raw materials in the bulk level to like particles and then atomic level. This is the from left side to right side is a top down approach. So for that you are supplying the energy. But if you go from right to left, this is a bottom up approach. At that time, energy released. You can see here two basic approaches to nanomaterials fabrication: top down from left to right and bottom up from right to left. So energy concept is also very important. This is the nanotechnology history. You can start from first cell with a nano machine. It is very old. At that time, the word nano was not very popular, but people were working in that field. Okay, and then 2004, Pentium processor based 90 nanometer technology. There are different types of technology in electronics also. It's progressing. You can see here in 1985, Robert F. Kull, Harold W. Grotto, Richard Smalley, they discovered the fullerene, the third allotrope of carbon, buckyballs. This is the third allotrope of carbon. And 1991, Professor Sumio Izima from NEC laboratory, he discovered carbon nanotubes during his observation under the TEM, transmission electron microscope. So here you can see the discovery of third allotrope of carbon, and it discovered by these three scientists, Kull, Grotto and Smalley. And the shape was designed by Buckminster Fuller. So by name of Buckminster Fuller, the name came fullerene. It has a 60 carbon atoms. Everyone knows about the carbon atomic weight is 12. Okay, and it has a 60 carbon atom. So when first time they synthesized and they did the experiment and they analyzed by mass spectrophotometer, at that time they got the result 720 AMU, atomic mass unit. So now it's very clear, 720 AMU, carbon atomic weight is 12. So this structure got 60 carbon atom and they discovered the fullerene, these three scientists. And you can see here, Buckminster fullerene is a tiny molecular cage of carbon having 60 atoms, making up the mathematical shape called truncated icosahedron. And this structure designated by architect Richard Buckminster Fuller, and that's why the name is fullerene. So first fullerene was synthesized by using laser ablation method. By using laser ablation method, the first fullerene was discovered. After that, many methods they employed, many scientists they applied many methods to synthesize the fullerene. But first synthesis was done by laser ablation method. After that, very well known, very popular method is laser evaporation method. That is same laser ablation method. You can see here the quartz tube is there. Quartz tube is there. Diameter is 20 millimeter, and at last you can get the deposited soot containing nanotube. And this method you can use for nanotube also. I'm not explaining in detail about the synthesis of carbon nanotube in laser ablation, but to get the knowledge about the laser ablation and laser evaporation method, I put here the schematic of the same method. Here is the furnace, so you can do the reaction here in argon gas atmosphere. Laser is there, you can see the pulse laser is a source, and then ultimately you can evaporate the material, and then with the help of laser, and it deposited at water cooled copper collector, and after deposition, after reaction, you have to cool down the whole system. Ultimately you are getting the material and we have to analyze it. This is the whole system of laser evaporation method. The discovery of carbon nanotubes is also a very good history. Professor Sumio Izima, they synthesized the fullerene by using the arc discharge method. And after his synthesis, he was observing the material under the transmission electron microscope. And during the observation, he found the elongated structure looked like fullerene, but it was elongated structure. And then he observed it is like a tube in nanometer, and then he gave the name nanotube. The tube itself has a nano diameter, and then he gave the name is a nanotube, and that was the first discovery of multi-wall carbon nanotubes. What he observed under the microscope, and it was the byproduct of fullerene synthesis, because he was doing the fullerene synthesis by using arc discharge method, not laser ablation method, but arc discharge method. This is also very popular method in the field of carbon materials, carbon nanomaterials especially. So at that time he got the carbon nanotube. We are learning, I know the nanomaterials, but for catalysis, we have to understand the concepts in the nanoscience and nanotechnology. Then we can talk directly how nanomaterials are so important in the field of catalysis. Before understanding about the nanomaterials, we cannot talk directly for the catalysis field. That's why I'm explaining first about the nanoscience, nanotechnology, nanomaterials, especially for fullerenes and carbon nanotubes. Let's see here, two types of systems have to be considered: single wall carbon nanotubes and multi-wall carbon nanotubes. The graphite, it has a graphene, one single layer of graphite is known as a graphene, and one can roll it in a seamless cylinder, and you can get the structure like a tube. And this is a single wall, that's why it's known as a single wall nanotube. If wall is increasing, if two wall, then is a double wall nanotube. If it is a more than three or four or five wall or multiple, then it's a multi-wall nanotubes. So here is the like a simulated image, pictorial presentation of single wall nanotube, double wall nanotube, and multi-wall nanotubes. So this is the real picture. You can see the reference here at the bottom. Professor Sumio Izima, he did the experiment in 1991, and he published the article in Nature. He reported in Nature, well-known, very popular journal. Synthesis of Carbon Nanotubes was the title, and this is the first TEM image of carbon nanotube, I can say multi-wall carbon nanotube. So how you observe under the microscope? For enhancing knowledge, just I am showing you, here are the cross section of those nanotubes. You can see here the scale is also there, 3 nanometer, but These are the walls in the cross section, but the real walls are here. So here more than, you can see here, this is the A, B and C. So when you talk about A, n is equal to 5. N is equal to 5, number of walls 5. N is equal to 2, number of walls 2. And it has a diameter also. Number of walls are 7 in the C. In the C, that is the image. And numbers are there, and he observed this one and reported in 1991, and that was the first discovery by Professor Sumio Izima for carbon nanotube, discovered and synthesized by using arc discharge method. So there are different characterizing techniques which can be used for the analysis of nanomaterials. I think everyone knows about that, so I'm not going to discuss in detail. ICP OES, IR spectroscopy, XRD, scanning electron microscopy with energy dispersive X-ray spectroscopy, TEM with EDX. Chemisorption is also very important technique to analyze the nanomaterials. TPR and TPD, temperature program reduction and temperature program desorption, is also very important technique. These two different techniques are very important. BET, BET is Brenner, Emmett and Taylor. They gave the techniques for getting the surface area, pore volume, pore size distribution. So this technique is very important. TGA, thermogravimetric analysis. It can give you the thermal behavior of different material. By this way, we can get the ideas how the nanomaterials can be utilized. By checking the properties, by analyzing them, we can get the idea that how the nanomaterials can be utilized. So here is the picture of scanning electron microscope, and this SCM is at our Department of Material Science, Sardar Patel University, and the nanomaterials can be visualized, can be observed under SCM also. This is scanning electron microscope, and it can be observed under transmission electron microscope also, TEM. And now the HRTM is also there, that is a high resolution transmission electron microscope. This is the optical microscope, but everyone knows about that. Optical microscope has 1000 or 1500 magnification, and it has a limitation. It is working on the light phenomena, but this is the working on the basis of electrical phenomena, and that's why it can go up to higher magnification. So scanning electron microscopy images are also there to get the idea. And you can see here, the scale is here, magnification is here, and you can see the different catalysis or catalyst particles are there. You can magnify this image and you can get the very good picture, and you can see the clearly the small particles are there on the surface. And by this way, at least you can get the idea by visualizing the material. This is the scanning electron microscopy image. With the scale from here to here is 200 nanometer. And you can see the small particles are sitting on the surface, or you can see the big lump of the material is there, and small particles are also you can observe. So by this way, at least we can get very clear idea how the surface morphology of particle or of any bulk material is there. You can see here transmission electron microscopy images. So by using transmission electron microscopy, we can get more idea with higher magnification. You can see now the scale is, this red line is 100 nanometer. Here also you can see. So you can get very clear idea about the particles are there on the surface with different contrast. And by this way, we can get the more idea about the nanoparticles, nanomaterials. These are the real pictures of scanning electron microscopic images and transmission electron microscope image of carbon nanotube. How it look like? you cannot recognize it is tube or fiber under SCM, because this scanning electron microscope is giving only surface examination results. That's why by using this SCM, we can see the nano size formation, but inside the hollow core is there or not. For to confirm that, we have to do the transmission electron microscopy analysis. And by this way, we can get the idea the the tubular structure is there or not for the same nanotube which we observed under the SCM. So by this way, it is fiber or not hollow inside or hollow inside. If hollow inside, then and then we can use the word or terminology as a tube, and that is in the nano dimension means general concept 1 to 100 nanometer. Then and then we can say it's a nanotube. Otherwise, sometime 500 nanometer dimension materials are also there, but we can consider it as a submicron, because 1 micrometer is equal to 1000 nanometer, So sometime 500 nanometer is a submicron size material. So you can see here different types of geometry and growth of carbon nanotubes. Sometime I synthesized in past bamboo shaped carbon nanotubes, and this is the real picture under the TEM, and it was reported long back in the International Journal of Nanoscience. So if we do the SCM EDX of nanoparticle of any material, but at least for nanoparticle, because my lecture is on that, my talk is on that, that's why I'm talking for that purpose only. If you do, you can see the surface examination under the SCM, but with EDX assembly, you can get different element, different color. So you can recognize different element with different color under the EDX attached with the SCM. By this way, you can get the idea that magnesium is present, iron is present, silicon is there with oxygen. By this way, you can get idea with different colors. Here, see here, nickel is also present, Fe is also present, magnesium is, and with this image, you can get the spectrum also. So you can have a very good idea about from the spectrum as well as images. STEM with EDX is also very important. This is not with SCM, this is with scanning transmission electron microscopy with EDX. So by this way, you can again recognize with the different colors of different element. Aluminium, green, silver, blue particles are there. You can see oxygen everywhere with the red, and these three images in color are the section of this area. So this area, first you observe and you put under the EDX, then you can recognize different element with different color, and by spectrum also you can get the idea how much it present in that specific area with the boundary. Deep pen lithography is very popular method. You can write in, you can say nano writing, nano font. Okay, see this one is 0 to 180 nanometer, and someone wrote NU, and this is the size of 15 nanometer by using this lithography technique. So that is also very good. Someone made, I'm giving you some fascinating world of nanoscience and nanotechnology. Some images are there to know. The world's smallest guitar, this 6-string guitar, is 10 micron. So someone made like this way also. And I think in the next slide you will get the more idea about the catalysis by using the nanomaterials. But because of some technical reason, I'm not showing you the different videos of nanoscience and nanotechnology. You can get the more idea from that video also. If possible, then organizer will show you at the last or at the end of my presentation. But now in the next slide, you will get the idea for how nanomaterials are working in the field of catalysis and how it is very much useful or important for the catalysis. As I mentioned just now, how nanomaterials are so important in the field of catalysis. But before we start that point, very fast, let we understand the applications of nanomaterials in different fields. It can be useful in chemical industry, automotive industry, medicines, energy sources, cosmetics. So each and every field, they have applications of nanomaterials. Here you can see the applications of nanomaterials in medicine. Very huge field of medicine. It is also applications of nanomaterials. But now, today, our main focus is on applications of nanomaterials in catalysis. The extremely small size of nanomaterials maximizes the surface area to volume ratio, as I mentioned. It exposed to the reactants, allowing more reactions to occur. The applications ranges from fuel cell to catalytic converters, photocatalytic devices. Everyone knows about that photocatalytic and catalytic converter. We are going to see, I think at the end of my talk, the catalytic converter application also. For the production of chemicals, nanozirconia, for carbon monoxide hydrogenation, for the isobutene synthesis. Now, in isobutene synthesis. So, by this way, in catalysis field, the applications of nanomaterials are there with different context. In communication, in electronics also, nanomaterials are there. This is very interesting, that's why I am showing you. Very fast, we'll cover few slides. It has a different idea of different nanomaterials in various fields if we talk about the applications. The bumps that make up the information on a CD are 0.5 micrometer wide. And the CD was now the old concept. People are using now DVD, pen drive, but the bumps that make up the information on DVD are 320 nanometers wide. That's why there is a large storage in the DVD. You can see the real picture of DVD surface. You can see here the real picture. Different nanomaterials have a different application in automobile field also. Here is the nanocatalyst, and membrane technologies will play critical role in making fuel cell economically viable and replacing the internal combustion engine. So people are more working on the catalytic converter, fuel cell. This type of fields are emerging fields nowadays, and by using the nanoparticles, you can see here uh, Airbus 380, about 20% composite material is there by using nanomaterials. You can see here fabric dressing. So silver nanoparticles provide powerful antiseptic properties. Everyone knows about the silver is antiseptic, but this nanoparticle of silver is also providing the antiseptic property, and people are going to, or they are using in this type of product. Everyone knows about the silver nano washing machine by Samsung. So if you put in the Google, the Samsung semi-automatic washing machine silver nano, it's coming. And now you can see here what they are. This is from Samsung website in 2017. Bacteria and fungus are removed 99.9 by silver nanoparticles. Therefore, no further proliferation of germs will be affected. They also try for that, and the product is there. Now you can see the washing machine here, and this is, I'm telling you very short, but here you can see now the lotus petals or leaves. The dirt cannot stick on the surface of lotus leaf. By using this same concept, scientists, researchers thought, and now you can see here this without any adhesion or stickiness, you can get the free flowing surface by like a lotus, because dirt cannot stick. So this one is a water repellent, that you can see the liquid on the surface. So surface will be always clean. Same concept they applied for the anti-fogging glass or self-cleaning glass, like now people are using in the civil construction a lot. That's why the self-cleaning glass has a more importance. Nanotextile, no dirt can stick on the cloth, so nanotextile is also very important concept. By this way, many applications are there in the field of composite, tennis racket, fishing rods, car body panels. They have a high strength and light weight, so people are using this concept also. Now I am going to talk on catalysis part. So the diesel additives called Envirox has developed by Oxonica, and that company from the University of Oxford. It consists tiny particles of cerium oxides which catalyze the combustion reaction between diesel and air. So cerium oxide they use as a nanoparticle. The cerium oxide functions as a kind of oxygen store. It releases oxygen to oxidize the carbon monoxides and hydrocarbon gases to form a carbon dioxide, and also absorbs the oxygen to reduce the quantities of harmful nitrogen oxides, greenhouse gas. So it's reducing that amount, and the result is a cleaner burn that converts more fuel to the carbon, carbon dioxide, produces less noxious exhaust, and deposit less carbon on the engine cylinder walls. This is very useful applications, and you can see the best example over the last few years. A bus company, Stagecoach in the UK, has been experimenting with using cerium oxide nanoparticles added to the diesel fuel, and it has been found that there was a 6% and 5% fuel saving respectively. Now the company uses this additive in over 6,000 buses. So this is the real example of nanoparticles, nanomaterials in the field of catalysis. So the ways to make chemical reaction faster, there are many ways. You can talk for temperature. By increasing temperature or by increasing the rate, you can enhance the reaction rate. Ultimately, you can get the results faster. The pressure is also a very important factor, like a temperature. But the disadvantage of temperature is too hot. We need a very high temperature sometime. Under pressure, or sometime for the pressure also disadvantage of explosion, as we heard many cases of explosion. You can add other chemicals to enhance the rate of reactions, but the disadvantage is to separate it out at the end of process of the chemicals. It's very lengthy. Sometimes it's very tough process, difficult to separate it out. And the fourth way to make a chemical reaction faster is the catalyst, or you can say catalysis. Sometimes the disadvantage is not all catalysts are costly, but some catalysts are very expensive. So we have to take care of that thing also in mind. So if you talk for catalysis, there is a physisorption, that is a physical adsorption, and chemisorption, that is a chemical adsorption. By not taking much time, here I want to tell you about this. Physisorption is usually take place at low temperature and decreases with increasing temperature. But this chemisorption, it takes place at higher temperature only. It requires activation energy for the chemisorption, and this physisorption does not require any activation energy. So to activate, we need, in chemisorption especially, we need some energy. Okay, so this is like, okay, fine. Chemisorption is a forces of attraction by chemical bond forces. Forces of attraction are there, kind of van der Waals forces in the case of physisorption, because it's a physical absorption. So it's a van der Waals kind of forces are there. So here the role of catalyst. Catalyst speed up the chemical reactions without being used up. That everyone knows now, these type of things we are learning from last many years from the school days. So I'm not talking in detail for this type of topic, but now the thing is, what is the catalyst? The name catalyst was coined by Berzelius in 1836. This is for information. According to the IUPAC, in 1976, a catalyst is a substance that being present in a small proportions increases the rate of attainment of chemical equilibrium without itself undergoing the chemical change. So you have to use in a small proportion, and it cannot undergoing any chemical change during the process, during its use or during its application, utilization. So catalysis is the increase in the rate of chemical reaction due to the participation of substance called a catalyst. So interdisciplinary approach, the catalysis is research in the catalysis deals with the chemistry, physics, material science, engineering, as well as in biology also. So what is catalysis? Catalysis is an action by catalyst, that is any kind of material which take part in a chemical reaction process and can alter the rate of reaction, and it itself will return to its original form without being consumed or destroyed at the end of the reaction. Already I talk on that topic. Three key aspects of the catalyst: action, taking part in the reaction. It will change itself during the process by interacting with other reactant and product molecules. We have to take care of that. Altering the rates of reactions, yes, always. Returning to its original form, yes, we need its original form back, otherwise, or it can sustain in the same form, otherwise there will be a big problem during the catalysis reaction. The types of catalysts are heterogeneous reaction, heterogeneous catalysis, homogeneous reaction, homogeneous catalysis. The enzymatic catalysis is also there, that is mainly connected with the biocatalysis. But in homogeneous, the catalyst is in the same phase as the reactants are. In the heterogeneous catalysis, the catalyst is in the different phase from the reactants. So this is very well known thing. We have to take care and we have to understand of this. Activation energy, the energy required to overcome the reaction barrier. Because to do the reaction, we need the energy in the system. And that's why you have to cross that barrier by using any form of energy. It can be temperature, pressure, by adding some other chemicals, or by catalysis. So here, without catalyst, you have to use more energy. But with the catalyst, yes, we are very much eager to know that without catalyst and with catalyst, what type of result we can get. But scientists found that without catalyst, we have to take more time, or we have to wait for more time, or sometimes no products at the end if no catalyst is there. So with the catalyst, it is very easy. Activation energy defined as a minimum energy required to start a chemical reaction. The activation energy of a reaction is usually denoted by the symbol and the given in units of kilojoules per mole. So catalyzed reaction have a lower activation energy, and that's why the rate limiting free energy of activation, and then the corresponding uncatalyzed reaction, then the corresponding, resulting in a higher reaction rate at the same temperature. The temperature conditions are similar. So here you can see metals, semiconductors, insulators, solid acids are different class of catalysis. Examples are in metal, platinum, palladium, iron, nickel, silver, copper. Oxides you can use as a catalyst. Insulators are also you can use as a catalyst. Solid acids, silica mostly you can use as a catalyst. Clay is very good example of aluminosilicate ceramic material. So that can be also used for a catalyst support or catalyst itself. So by using the metals as a catalyst, we can do hydrogenation, dehydrogenation, hydrogenolysis, isomerization, cyclization. These type of reactions are there By insulators, by using these aluminum oxides, silica, magnesium oxide, we can do the dehydration reactions. Cracking, we can do by using this silica, magnesium oxide, zeolites. These type of all reactions are connected with the different types of catalyst material. So here you can see the catalytic reactions in heterogeneous system, especially in heterogeneous system, different phases of catalyst are there. So here diffusion occurs on the surface, diffusion of the reactant to the catalyst, then adsorption take place. You can see here diffusion and reaction in the step 3 and 4, and at last desorption of reaction products are there. So the progress of heterogeneous catalytic reaction can be resolved into at least 5 distinct steps. Diffusion of the reactant to the catalyst, diffusion of the reactant to the catalyst. On the surface of the catalyst, it can diffuse. Adsorption of reactant on the surface. The chemical changes on the surface, formation of the adsorb complex, and the decomposition of the adsorb complex is possible, and it can be converted into product. And then desorption and diffusion of the reaction products from the catalyst. At last, you can get the separate product from the catalyst. So the example, hydrogenation of carbon-carbon double bond. You can see a very popular example. At last, you can get the alkane by hydrogenation of alkene, and the catalyst you have to use is a nickel. The simplest example of this reaction between the ethene and hydrogen in the presence of nickel catalyst. In practice, this is the pointless reaction because you are converting the extremely useful ethene into relatively useless ethane. Ethene hydrogenation is widely used as a reaction test of new hydrogenation catalyst. This can be possible sometime. So criteria for the good catalyst are, it can have a good activity, selectivity, stability. So this is most important criteria for the good catalyst: activity, selectivity, and stability. Non-chemical, if you consider under the non-chemical category, the morphology of the catalyst should be very good. It has a good mechanical strength because during reaction, if it can break in smaller particles, and sometimes it can die during the reaction. So no productivity is there, and cost is also very important factor when we talk about economically viable industrial world. So by this way, activity, selectivity, I'm not okay. Let's talk. Activity is the ability of catalyst to accelerate the chemical reaction. How much it convert from the reactant. That in terms of mole percentage or like that is activity. So that is only for transformation. And the selective productivity is how much is converted and how much selectivity you got from your desired product. For your desired product, how much selectivity you got. So that is selectivity is the ability of catalyst to direct reaction to yield particular product. How much it converted, that is related with the activity, percentage conversion. But selectivity is related with the how much you got your desired product, that is related with the selectivity. But in the era of 21st century, the researchers are trying hard to achieve maximum selectivity for desired product. For desired product, we need maximum selectivity. If sometime converted product is from reactant is around 50%, but selectivity is around 99%. That's very good. 90%, that's very good. So now people are concentrating for more selectivity in this era. So catalyst design, then you have to take care of mechanical properties, strength, surface area, porosity, acidity. These all properties or characteristics related for the catalyst. Catalytic properties, as I just discussed now, activity, selectivity, stability. Chemical, physical properties. So active phase is always there. In heterogeneous catalyst, support has a very good role. If support has a high surface area, optimum surface area for the reaction, then you can get very good productivity, very good yield at the end of your whatever reaction in your system. Promoter, sometimes we have to use the promoter to promote the reaction with the catalyst. So there are typical heterogeneous catalysts are there. So active phase, promoter and carrier support. Here examples are there. Material is metal, metal oxide, metal sulfides. You can see the platinum, palladium, these are the active phase in the catalyst. Support, you can use different oxides, metal oxides, like you can consider as a ceramic material, aluminum oxide, silica, titania, zeolites, clay. These all are support. It providing support to disperse this metal particle. So the high surface area support is very good because the good dispersion we can get by using high surface area support. A good dispersion of metal particles that can be nanoparticle also. So why supported catalyst? Just now I mentioned with support no sintering occurs because sintering is very dangerous in catalysis. So without support, you can see here all particles agglomerated. If all particles agglomerated, then there will be a no activity of catalyst. So if with the support, we have a higher surface area and these black particles of metal, it can easily dispersed on the support and we can get very good active site for the reaction. Active site is like a seed, is like a seed. It can help to convert reactant to desired product if your system is optimized. Supported catalyst possess active surface area, no rapid sintering, uniform dispersion tends active sites. As I just mentioned, uniform dispersion tends active site. So no rapid sintering can happen. Higher selectivity and at last good activity results means good conversion is also possible with the desired product selectivity. So this is very important concept when you talk about supported catalyst. The selection of the support is based on the series of desirable characteristics. Stability on the reaction, appropriate physical form in the reactor, adequate mechanical properties, because if sometime you have to work under pressure also. So your catalyst is under pressure, your reaction is going on under pressure. At that time, the stability, mechanical stability of catalyst at that temperature and pressure is most important. High surface area and porosity. It's very important factor, inertness of catalyst. It cannot be it cannot be mixed with your reactant. Otherwise, the inertness will go and it can mix, then you can get the impurity at last in your product. So chemical nature is most important. So some supports are very popular. Activated carbon. Activated carbon is highly porous carbon. Zeolite, activated clays, activated alumina, Kieselguhr. These all are very popular supports people are using in the field of catalyst, which has a higher surface area. Surface area unit is meter square per gram. This is the unit of surface area. Please remember, by using the BET instruments, we can get this surface area, pore volume, pore diameter of different support and different catalysis system. So pore size breakdown, macropores are there, mesopores are there, micropores are there. If your pores are, for example, less than 2 nanometer size, then these pores are micropores. If your pores are from 2 nanometer to 50 nanometer in diameter, these are mesopores. And pores are more than 50 nanometer diameter, they are considering as a macropores. So you can see here macropore more than 50 nanometer diameter and mesopores 2 to 50 nanometer and less than 2 nanometer diameter is micropore. So this is very important concept. On the support, you are dispersing the metal and this support has a porosity. This porosity help for that dispersion with the surface area. So surface area and porosity size and porosity volume and the distribution of porosity. These all are very important factors related with the catalyst geometry. You can see the schematic of platinum supported on alumina. So platinum particles, black particles are supported on the surface of alumina. So here active catalyst phases reaction typically catalyze the different reactions. So here hydrogenation, steam reformings, these type of reactions, catalyzed reactions possible. Fischer-Tropsch synthesis by using this type of elements and compounds. You can make the compounds from this metal also. By using this oxide, we can do the partial oxidation of hydrocarbons or and CO. Acid catalyzed reaction can be possible by using this type of metal catalyst. Sulfides are very useful for hydrotreating. This type of reaction, hydrogenation also we can do by using sulfides as a catalyst. Carbides are also very useful for hydrogenation, Fischer-Tropsch synthesis. This type of catalyst systems are specific catalyst system used for specific type of reactions. So chemical properties, we are not going in detail for this slide, but for your information, I am telling you properties of catalyst are chemical properties as well as dynamic properties, and these dynamic properties are related with the catalyst. In short, we can tell chemical properties are acidity, oxidation state, chemical structure, chemisorption nature, etc. And this dynamic related with the catalytic properties, these can be catalytic activity, selectivity, stability, specific activity. So here adsorption desorption technique in the catalyst characterization, active site surface area most important, temperature program reduction as I mentioned before, TPR, it can give you reduction degree of active sites, activation energy related to the reduction. Temperature program oxidation is also there, TPO analysis, it can give you oxidation degree of active site. If your metal particles are there on the support surface, it can give you idea about the reduction as well as oxidation, redox reaction you can say, it can give you the idea. And desorption is also there, it's known as a temperature program desorption method, TPD. So general scheme of catalyst characterization, there are many methods to characterize the nanomaterials, nanocatalysis. As I mentioned before, the all characterization techniques are most important. By using the sophisticated instrument, we can do it. One should be aware of poisoning, coking, and sintering in the catalysis field. This turnover number is most important, This turnover number is most important parameter. You can see the turnover number and turnover frequency. Turnover number is the molar ratio of converted substrate to catalyst. Converted substrate to catalyst. This is the turnover number. Turnover frequency is turnover number per time, per minute or per hour. So for example, 10 millimoles of substrate are converted to product using a catalyst loading of 0.2 millimoles in 2 hours. So turnover number is 10. The catalyst loading of 0.2 millimoles, 0.2 is equal to 50. This is the number. Turnover frequency is the 50 and divided by the reaction time for 2 hours. So you can get the turnover frequency 25 hour inverse. So we have to remember the SI unit of measuring the catalytic activity of a catalyst is the catal, which is moles per second. The productivity of catalyst, this is very important, can be described by the turnover number in industry, especially in lab also, but industrial people, they always talk about turnover number and turnover frequency. So the productivity of catalyst can be described by turnover number and the catalytic activity by the turnover frequency, which is turnover number per unit time. So the catalysis is most important. Nowadays catalyst, we always talk about catalyst in the chemical industry. So accelerate the reactions by order of magnitude. I'm not taking much time to understand why catalysis is so important. We all know about this, but this is the link link between the two topic. That's why I put the slide here. See here, in this way, the efficient catalyst in combination with optimized reactor and total plant design are the key factor in reducing both the investment and operation cost of a chemical process. So by this way, the nano catalyst come in the picture, and by using the nano catalyst with extremely small size, surface area to volume ratio we can increase, and this is very important parameter. You can see here the conventional catalyst were there, people are using steel also, but by using this newly developed catalyst, the base material with a high surface area support, we can get very good dispersion of nanoparticles on the support. Why nanocatalyst? Because of this reason. If more dispersion, very good dispersion, uniform dispersion is there, we can get very good active site, and it can help for the good catalysis reactions. So different type of nanocatalysis, high activity, high selectivity, excellent stability. These are the all advantages of nanomaterials in the field of catalysis. So heterogeneous catalysis, excellent stability, easy accessibility, easy separable, and these all are advantages of nanomaterials. So the shape effect, the size effect, the interparticle distance effect because of dispersion, confinement effect, oxidation state effect we can get by using these nanomaterials in the field of catalysis. So nanocatalysis, by using nanomaterials in the field of catalysis, you can call nanocatalysis. These are the very good advantage: improved economy, energy efficiency, reduced global warming, wastewater treatment, many fields are there. So by using these nanomaterials in the field of catalysis, there are many methods by which we can synthesize the nanocatalyst. As I discussed, top down and bottom up. Here also different examples of different methods which can be very useful to synthesize nanoparticles. Everyone knows about their sol gel, precipitation method, sonochemistry, microemulsion. Okay, by this way, nanoparticles are most important in the field of nanocatalyst. Gold, palladium, copper, zinc oxide, silver. So you can see the different reactions are there. Synthesis of highly substituted pyridines, synthesis of 1,2,3 triazole by using the gold. This type of deoxygenation of epoxides, this type of reaction we can do by nanocatalysis. Because of short of time, I have to go a little bit faster, and let's see now automotive emission control. So automotive emission control is very good applications in the catalyst field. By using this catalyst, you can see here, by using this type of catalyst like a palladium and palladium, we can do very good reactions of different hydrocarbon, carbon monoxide and nitrogen oxides. So by reducing nitrogen oxide in nitrogen, by oxidizing carbon monoxide in carbon dioxide, by this type of reaction, we can increase the probability of clean and green environment. So this catalytic converter is very important concept of catalysis, and we can say the two-way catalysis is also there, three-way catalysis is also there, and this is the exhaust manifold in the automotive system, in the car and everywhere. The oxygen sensor is also there, the exhaust pipe is there, and this whole system is for that catalytic converter. These nanoparticles are present in three-way catalytic converter. By using this nanoparticle, means nanocatalysis, we can get very good result at the end in the form of H2O, CO2, nitrogen and oxygen. So these important gases we can get from the hazardous gas. These all are hazardous, and by converting them to useful gas, we can, this is very good concept of catalytic reduction and oxidation. So here the best example of catalysis is fuel cell stack. So here also you can see the catalysts are there. We'll take a little bit 2 or 3 minutes to finish my talk. Hydrogen fuel cell is most important. You can see here this red color hydrogen Yes, and then it's producing the electron, and then we can get the energy, and the emission is air and water vapor. So it is very green concept. It is very green concept by using the fuel cell, and the catalyst is there. At last, I would like to convey the message that today we have seen nanomaterials and heterogeneous catalysis. So if we take the example like a nanocatalysis system or nanocatalyst, in that the materials are in the nano size. So nano means small. How can? Small in terms of size. Then small means big. Big in terms of properties. Okay? And big means beautiful. Beautiful in terms of very good applications. These all materials have very good applications. Today, we have seen only one field, that is a heterogeneous catalysis. But as you have seen in nanomaterials introduction and property and application part, that nanomaterials have a wide range of applications, wide range of applications. So we can say the applications are very good. With this message, I would like to convey that the government of India in May 2007 has approved the launch of a mission on nanoscience and technology that is known as Nano Mission. Now, as far as the nanotechnology is concerned, we can see here from the BCC research report in December 2021, the global nanotechnology market should grow from $5.2 billion in 2021 to $23.6 billion by 2026 at compound annual growth rate of 35.5% for the period of 2021 to 2026. I think this is a very good information for all of us. At last, I would like to thank you for listening this talk, and this heterogeneous catalysis by using these nanomaterials is a very good approach, and it's a green approach also.